Today, we're going to discuss a classic sort of problem in physics called an Atwood machine. An Atwood machine is basically two blocks that hang from strings that are connected by a pulley. And the main problem is to try to determine the way that those blocks move. For this lesson, there are a couple prerequisites that I'm going to assume that the listener is familiar with. In this case, those prerequisites are Newton's second law, which states that the net force or total force on an object is equal to the product of the mass of that object and the resulting acceleration of that object. And the second prerequisite that we'll use as well is the formula for the gravitational force, also known as weight. The gravitational force is equal to the mass of an object times the gravitational acceleration, which on Earth is 9.8 meters per second squared. We'll use those facts for this problem. In our case here, the problem is to determine the acceleration of the block and pulley setup below, presume a massless pulley, and ignore friction. A massless pulley in this case just means that this part, the pulley, the thing that rotates without any effects on the forces that are going through the strings. Essentially, we won't really consider the pulley itself for the purposes of this problem, but in a more complicated setup that could be incorporated later. And we're going to ignore friction, meaning that we're not really going to account for any sort of outside influences affecting what's going on. We want to keep this particular example as simple as possible so that we can really get to the core of what's going on and not make it so complicated by having all of these additional considerations. In this particular situation here, we have two blocks that are labeled with M1 and M2. Those are the two masses of the blocks, and they're both hanging from one single string that goes around the pulley here. For our purposes here, let's presume that the mass on the left is larger than the mass on the right. So let's presume that the left block is going to go down and the right one's going to go up. Let's say we're releasing this from rest. The left one's going to be heavier, and so it's going to kind of want to go down while the right one goes up. In such a case, the acceleration of the block on the left would then be downward like this. So I'll label that as the acceleration A. Since these two blocks are connected together by a string, however one moves in the downward direction, the other one's going to move in the same way in the upward direction. So it's going to have the same acceleration, just pointed upwards this time. Okay, so that's the situation as far as acceleration is concerned in this setup. Let's also label the forces. And the fact that we're using forces is kind of hinted with the prerequisites because I did mention we need Newton's second law and the gravitational force equation in order to work this out. And typically when we have situations where there are forces acting, particularly unbalanced forces, we can use those individual force vectors as a way to figure out the acceleration. So let's think about the forces that are acting on each block. For the block on the left, mass 1, we, of course, have a gravitational force down. That's non-negotiable if we're on Earth. So we have a gravitational force going this way. That gravitational force has a value that's given by the gravitational force formula. It's the mass of the object times g. G is always the same constant value as long as you're on the surface of the Earth. So that's g, but the mass here in this case is m1. So I'm going to write m1 g like this to indicate that gravitational force down. The situation is exactly the same for the other block, so I'm going to label it like this here, m2g. And in this case, remember that we are presuming that m1 is the heavier block, so that force is going to be a little bit stronger than the one on the right. Now, those are not the only forces that are acting. We, of course, have the string that's interacting with each of the blocks. And the string is going to exert a tension force. Tension forces always act along the direction of the string. So for mass 1, that string is pulling upwards on the left-hand side, and also the same for mass 2. So we can label the tension forces. I'm going to use T to indicate the tension force. That's a variable indicating the strength of the tension force, pulling upwards on both sides. Now, here, those tension forces are going to be exactly the same. One thing that pulleys do a really good job of is redirecting force. So whatever the tension force is on the left-hand side, that's going to be redirected through the string around the pulley, and it's going to be the same tension force on the right-hand side. If the pulley had some mass, if we had some friction, those two tensions wouldn't be exactly equal. But assuming that the pulley has no mass and that there's no friction involved, those two tensions, we can regard those as the same very comfortably. So now at this point, we need to apply Newton's second law in order to relate those forces to the accelerations of each of the blocks. Since there are two different blocks, we're going to have two Newton's second law equations, and then that's going to be a system of equations that we're then going to solve in order to determine the acceleration, which is what we're asked to find here in this problem. So let's begin with the block on the left. On the left, the acceleration is pointing downwards. The direction that the acceleration is in, that's the direction that we should regard as the positive direction when we apply Newton's second law. So what I mean by that in this case is that the downward direction here, this is going to be our positive direction, and the upward direction is going to be negative. Again, that's determined because of the acceleration. The acceleration is down, so that tells us which direction should be positive for that block. So writing down our Newton's second law equation for the M1 block, we see that we have F net equals MA. I'm going to just go ahead and write that as M1A for that block. The net force is going to be the positive force and then minus the negative force. So in our case here, the positive force is the M1G. That's the gravitational force. And we're going to subtract away that magnitude of the tension force, T. That's going to equal M1A. So that's our equation that relates together the variables for the M1 block. For the M2 block, it's a little bit backwards in the sense that acceleration is upwards this time. So we're going to regard upwards as positive. Downwards here is going to be negative. That's just the convention that's necessary in order for that Newton's second law equation to work out and give us the correct result. So let's go ahead and do the M2 block. We have F net equals M2A. And then for the net forces, we have a positive tension, negative M2G. Okay, so that's what we have so far, and we're now left with a system of equations. This system of equations consists of these two final results that we got for each block, and each of those equations has two unknowns. Remember that M1 and M2 are given. G is also known here. The only things that we really don't know or that we could figure out from the given information is the unknown amount of tension and the unknown acceleration. Now, the unknown acceleration is the thing that we're asked to look for. So ideally, we're going to want to get rid of that unknown tension variable. Now, fortunately, there's a really easy way to do that. I'm just going to stack these two equations on top of each other. And in this case, if we add those equations together, let me do this here. If we add those two equations together, we can see that the left-hand side has a t and also a negative t. Positive t minus t is going to cancel away. So these two go away, and so all we're going to have is the M1G and the M2G on the left-hand side. So writing that out, for the left-hand side, we have M1G minus M2G, and on the right-hand side, nothing cancels. We just have M1A plus M2A. So now we have eliminated t. We have gotten rid of the variable that we don't know about, and we just want to find acceleration, which is one that we care about. That's the unknown that we want to find. So in order to do that, we can factor out the a on the right-hand side. To clean things up a little bit, I'm also going to factor out the g on the left-hand side as well. So I'm going to factor out the g, m1 minus m2 times g. On the right-hand side, I'm going to factor out the a the same way, m1 plus m2, a like this. So then we can solve for a just by dividing out this factor here, m1 plus m2. And so that gives us m1 minus m2 divided by m1 plus m2. I'm going to keep that as its own little fraction there, along with the g. That's our resulting expression for the a. So I basically took this here and I divided it by the m1 plus m2g. So here's that box part over there, and I divided that by m1 plus m2g, just rearranged it in a way that's a little bit more tidy, that keeps all the masses together, and then the gravitational acceleration is on the right there. This is then our final answer. So depending on whatever masses that you have, you can plug it into that equation and the acceleration will be computable based on that formula. So without really even knowing the exact numerical values of the masses, we can get a relationship that would allow us to determine the acceleration every time. One other thing that's kind of neat about an expression like this is we can check it with our intuition in a couple different ways. So for example, one thing that we could try to check mentally is what would happen if m1 equals m2. I know originally we assumed that m1 is larger, but there was nothing mathematically that we did that really required that. So we can think of a sample situation where m1 equals m2. If m1 equals m2, those two masses are going to be the same mass. And if they start from rest, our expectation is that neither of them would move, really. If they're starting from rest, they're just going to stay at rest because there's a sense of balance there. And what happens in our equation, if m1 equals m2, up here, m1 minus m2, that's going to be 0. And if that's 0, that's going to make the entire expression 0. So the acceleration overall is going to be 0 like that. So that's encouraging. One other thing that we can try is maybe seeing what happens if one of the masses is 0. So let's say, for example, that m1 was heavier than m2. But let's say that m2 was 0 kilograms. It had no mass whatsoever. Let's see what happens if m2 is equal to 0. In that case, if m2, if there's no mass on the right-hand side, that left-hand side one is going to fall just like it's in free fall. If we plug that into the equation here, if m2 is 0, so those terms go away. We have m1 over m1, which is just 1. And then it's 1 times g. So the acceleration is just g. And so that means that it's basically in free fall because that gravitational acceleration represents the acceleration of an object when it's just in free fall. So that also checks out. That makes sense. So that's our formula. That's a result of this problem. And thanks for watching.